続いては、マイクロソフト RPC およびコムでのクロスサーバー Xrefs の自動ハンティングについて、サイ・チェンさん、ヨンチン・ヒさん、ジャイミン・ワンさんからご紹介をいただきます。サイさんたちは中国のセキュリティ専門家。それぞれ侵入テスト、Web セキュリティ、Windows セキュリティを専門にしておられるようです。今回のテーマについて動画をいただいております。どうぞ皆様ご覧ください。
Hello everyone, today let's talk about cross-server Xrefs in COM and MSRPC and how to find them automatically. And this is our biographies. About me, my name is Chen Sai. I'm interested in Windows security and I studied web security in college. I'm also the speaker of Power of Community 2018. Now I work for MidSeek Technology Company. MidSeek offers penetration testing, security training, and other services to our clients. And the core members of MidSeek are all from Cyclover Security. Team Cyclover is a student team of Chengdu University of Information Technology. Our members have worked for Alibaba, Tencent, Qihoo 360, BitDance, Ant Financial, and other companies. Today we will begin with an introduction to MSRPC and COM, followed by the concept of cross-server Xrefs and some attack surfaces, and finally the algorithm. About MSRPC, it's a kind of remote procedure code defined by Microsoft. The interface exposed by the server contains a set of RPC routines that can be called remotely by the client. The client calls the stub code in its own address space, and then the stub and the RPC runtime library handle communication, parameter marshalling and unmarshalling, and calling the actual function implementation. And this figure roughly shows how MSRPC works. It is also easier for developers to embed MSRPC into their applications. Use IDL or Interface Definition Language to define the interface, and use the MIDL compiler provided by Microsoft to generate the stub code. Application source code only needs to include stubs and compile to use MSRPC. Next, we will discuss the COM. There is an anti-joke on this page. The object ref is a structure used in COM, which uses a fixed MEOW string as its signature. I don't know what MEOW represents, but when I saw it for the first time, all I could think of was the meow of a cute cat. COM acts as the glue between components. Binary components developed in different languages interact through COM, and they follow the same binary interface defined by COM. As you can see, the memory layout of a COM object starts with a pointer to a vtable, and followed by some custom data. You may be familiar with this, which is very similar to the layout of C++ classes with virtual functions. The similarity makes C++ easy to develop COM components. The client does not interact directly with the COM object, but interacts with the interface and calls the interface methods. Each interface directly or indirectly inherits from IUnknown interface, so includes 3 IUnknown functions for resource management and type conversion. They are query interface, addref, and release. For an object, it may have limitations on concurrency and reentrancing. The apartment connects them. An object resides in an apartment. If a thread wants to access the object, it must comply with the apartment's rules. For example, the rules do not allow multiple threads to access the object at the same time. To use COM, the thread must enter an apartment, and if it is in a different apartment from the object, the thread code needs to access the object through a proxy. There are 3 apartment thread models: STA, MTA, and NTA. For single threaded apartment, only one thread at a time is allowed to execute interface methods, so there is no need to handle thread synchronization manually. A process can contain more than one STA. With MTA, multiple threads can execute methods concurrently. There is only one MTA per process. The COM server can be in process, and its binary form is usually a DLL, while out-of process components runs in a separate process. Therefore, out-of-process components can have finer security configurations such as activation, access, and the user context in which the server process runs. After introducing RPC and COM, we will show an example of a logic bug that occurs in COM. This example is an arbitrary file reading vulnerability in the ActiveX installer device. This privileged device is a COM component, and one of its interface methods checks whether the user can open the ActiveX component specified by him and copy it to a directory that is allowed to be read by normal users by default. As shown in the figure above, the check logic is impersonating the user's identity and calling createFile API to obtain the file handle. If the handle is valid, the original identifier is restored and the file is copied. So there is a time of check to time of use bug. We can use the symbolic link switching technique introduced by James Forshaw, which uses normal user readable files to pass the check and then switches the target of the symbolic link to any privileged user readable file. The final file copy operation in this example uses the copyFile API. Therefore, we usually automatically search the core chain from the entry function to the copy file, and then manually reverse engineer to determine whether there is a bug. With a disassembler like IDA Pro, finding the core chain is easy. But sometimes, the actual operation is located in another server, and the server called by the client acts as a client of the other server, which is a cross-server Xrefs, since it crosses the boundary of multiple binary files. And by the way, in fact, it is not necessarily a file boundary or even a process boundary, but I cannot find a term that fits it. But whatever, the built-in cross-reference function of the disassembler is no longer valid, because we can only find the core chain to COM or RPC API. Cross-server Xrefs has these scenarios, and C for COM, R for RPC, so C2C, R2R, C2R, and R2C. I mentioned that crossing the server boundary does not necessarily cross the process boundary. In COM, I think the smaller unit is an apartment. A COM object holds an interface pointer to an object residing in a different apartment. Let us call it the outer object, and the contained object is the inner object. We discussed the cross-server scenario. Now let us discuss topics related to security. The server may wish to know the identity of the client token during the call. As shown in the figure, Command RPC provides the impersonation feature, which can temporarily convert the server thread token to the client, and then the thread can retrieve the information in its thread token or perform security checks as a client. Consider the identity passed in the cross-server call. In MSRPC, it seems natural that the intermediate server acting as a proxy projects the identity of the original client to the upstream server. Sometimes, an intermediate server that is not impersonated calls an upstream server that performs sensitive operations in impersonation context. And because the identity of the original client is not projected, a vulnerability may occur. And this is the bug class in MSRPC cross-server calls disclosed by James Forshaw. MSRPC allows developers to specify a security callback function, which is used to determine whether the client is allowed to call interface routines. By default, after the client passes a check, it will not check subsequent calls with the same token modified ID. This behavior is controlled by the RPC signal cache flag of the flags parameter. Therefore, the code logic of the security callback is worth checking. Some codes are vulnerable, such as checking whether the client PID and the PID of a trusted process that an attacker can call are equal. In this case, the attacker's second direct call to the final server will no longer be checked. If the interface routine performs sensitive operations, it is very dangerous. Back to impersonation. The phenomenon in COM may be a bit counterintuitive. By default, even if the thread calling the COM method has been impersonated, the identity projected to the upstream server is still the process identity. So when clocking is enabled, it seems more intuitive. For cross-apartment calls, if the clocking is not enabled, the inner object will obtain the different call context information from the outer object. Assume that the inner object does not use the free-threaded marshaller, so there must be a proxy. If the internal object wants to check whether the caller is a container process or retrieve other token information, it will obtain the process context of the outer object, not the original client, so a security bug may occur. Let's talk about clocking now. There are two types of clocking, static and dynamic. The main difference between them is whether the identity will be cached. To enable clocking, you can call the COM API COM-initialized security, which is enabled process-wide, while COM set proxy blanket enables clocking on the specified proxy. If you don't use impersonation, the clocking is useless. Clocking is not enabled by default, as mentioned before. With respect to choosing identity to the project to the upstream server, select the thread token if it exists, otherwise select the process token. And this rule applies to both types of clocking. Client always calls the interface method on the proxy, so the identity bound to the proxy is presented to the server. For example, if the upstream server impersonates the client, it will switch to a token bound to the proxy. For static clocking, the proxy identity is cached. If clocking is set using COM-initialized security, the first time a method is invoked on the proxy picks up the token and the identity does not change on subsequent calls. If you use COM set proxy blanket or core set blanket method of iServer security interface, the thread or process token is selected at this moment. For dynamic clocking, the token is selected during each calling. If we create the same instance twice in the same apartment and the interface pointer that should be released for the first time is not released, as shown above, then sometimes we will find that some COM classes return the same interface proxy. For this kind of COM class, in the crossover call, it is assumed that the static clocking is enabled using COM-initialized security, and that the outer objects always have external references. If method delegates the interface method to the inner object and forget to release the interface pointer at the end of the call, the identity of the interface proxy of the inner object will be cached at the first call, and the same proxy will be returned every time concrete instance is called. Therefore, subsequent call use the same identifier. And this means that if the attacker can induce the user call the interface method for the first time, he will be able to call the method as the same user in the future, and this is an identity fixation attack. It's annoying to manually find cross-server scenarios for happy life without automation. In this section, I will introduce how to search the RPC server and client interface routines, COM interface method, and COM clients so that we can trace the cross-server core chain. The algorithm we will introduce still have flaws, mainly because it is difficult to solve the analysis of COM client calls. So if anyone here has a better idea, I want to learn from you. And in addition, most of our ideas are based on static analysis. Searching for RPC interface routines, tools such as Find RPC have shown effective methods. And basically, we obtain the RPC server interface structure through brute force search, as we analyze other related structures to obtain an array of routine pointers and interface information. We may be interested in any ideal combination options. For example, we need to recombine the ideal code generated by RPC view or anti-object manager. The dispatch function in the dispatch table can provide us with some clues. For the fully interpreted mode, the OI option uses NDR server call, while OIF uses NDR server call 2. If the specified transfer syntax is NDR64, use NDR server call NDR64. For inline stop mode, use the OS page to combine, and the interpreter info field of RPC server interface is a non-pointer. For a protocol switch, in addition to the DCE and NDR64 transfer syntax, you can also specify the OR parameter. Depending on the environment, the OR parameter will generate different stubs. For 32-bit stubs, the transfer syntax is almost the same as DCE. For determining whether it is a 64-bit stub, we can check the flags, uncount, and dispatch functions as shown in the figure above. Now we have found the RPC interface routines and know the combination options, which are basically server-side information. And next, we want to find the client and try functions. They have almost the same prototypes as the server routines and are called by the client application code. The sub-array function in this figure is an example. Obviously, it can also be called by another server routine, which is what we call the cross-server Xrefs in real. But how do we know which routine in which server interface it represents? At least two pieces of information are required: the interface ID and the index of the routine pointer array. This index is also called the procedure number. For the interface ID, if we parse thousands of executable files in Windows, we can create an interface information database and find the associated server-side interface by querying the interface ID in the database. Now the question is translated into how to extract the interface ID and procedure number from the client routine. Let me talk about the conclusion first. The first and second parameters of NDR client core 2 provide us with this information. These two parameters point to initialize static constants, so we can statically analyze their addresses. As that static analysis of their addresses, more precisely, we need to statically obtain the constant values of the first two parameters of NDR client core 2, which are the addresses of the key data structures. Okay, let MetaSp come on stage. It will solve our problems. MetaSp is a cross-architecture assembler, disassembler, combiner, linker, and debugger written in pure Ruby. It has a great feature, backtracking. To demonstrate the backtracking, suppose we want to know the value of the EAX register after executing the shellcode in this figure. MetaSp traces the instruction that affects the EAX value from the last instruction forward to get the result, and in this case, jump EAX. So each decoded instruction has a binding, which records the change of variables before and after execution. This is the output of the sample script. You can see that for the instruction push EAX, the execution will affect the ESP register, and the top of the stack will be written to the value of EAX. and in the end, MetaTask gained the value of EAX. The value does not have to be a constant, but can be a symbolic value, such as EAX at 8. After all, the process of evaluating variables may depend on runtime results. This technique is useful for determining the parameter values of a function call. Therefore, backtracking first and second parameters of NDR client core 2 can obtain the addresses of stub descriptor and procedural format string, which is the cornerstone of analyzing the interface ID and procedural number. Then parsing the stub descriptor can get the interface ID. Simple as that. According to the combination options, finding the procedural number involves two cases. In all protocol and 64-bit environment, the client entry point is NDR client core 3. Its second argument is the procedural number, so backtrack it. In the other case, we need to parse the procedural format string. Format string are consumed by the NDR engine, and procedural format string describes routines, parameter types, RPC options, and other information, but we only want to know the procedural number. And this figure depicts the layout of format string and location of the procedural number. Once all the above is done, we should know which server-side routines the client routines map to. Backtracking is also useful to help search for instances of certain bug classes. We discussed the RPC security callback function earlier. The function pointer pointing to the function implementation is a fixed value after compilation, so we can find it and disassemble it. We can also know whether caching is enabled and information about registered interfaces. As you may remember, I mentioned that callback function that checks the PID of the client process may cause security bug. Through backtracking, automatic search for such vulnerabilities becomes feasible. Now, let's talk about the common part. As far as I know, it is almost impossible to statically search a address of a COM interface method. We usually need to create the object first. The first method is to hook NDR stub core 2 or 3, which is useful for standard marshaller. For RPC calls, the PZ's parameter is a pointer to the standard interface stub, and the PV server object member field of the interface stub points to the interface. The second method is to use event tracing, and we focus on the method address and interface point fields in the server sync call start and server async call start events. James Forshall's method basically relies on public symbols to parse the OID and IP ID databases in the COM process to obtain the interface pointers. And this method is implemented in OLEview.net, and we recommend using it. Compared to searching for RPC clients, finding COM clients is a real challenge. The most difficult problem is how to know where the interface methods are called. When the client calls the object activation API, like concrete instance, you can use backtracking to easily find the COM class ID and interface ID, but the value of the interface pointer returned is determined at runtime and may point to heap memory. If you backtrack, you will only get a symbolic value such as ESP at 8 in brackets. In general, it is difficult to know when the interface pointer is accessed because all calls to methods are indirect. We have a solution that is not so powerful, and it is definitely a semi-finished ideal. Limiting the address space of the hypothetical method call to the same function as the activation API is naive, but is more efficient. When we find the call side to activation API, we search backwards for the indirect calls until the function returns the backtracking vtip pointer. Here is Rx register and record the value of the dereferenced pointer. Then we backtrack interface pointer from the activation API and compare them. If they are the same, we find a potential call to the interface method. We can also do some auxiliary checks. For example, the first parameter of calling the call method is an interface pointer, which can also be used for comparison. Note that in our example, we assume that control flow guard is disabled, so the code for indirect calls is clear. But this is not always the case. For example, almost all built-in servers of Windows 10 have CFG enabled. The theory is very boring, huh? And we all like tools. So I prepared a small toy, the TurboX library. I spent several months developing it. Here are some of its features. Since I'm lazy and many functions are not perfect, I suggest you treat it as a proof of concept I'm talking about today. And by the way, it runs very slowly, so hope it won't make you wait until the universe big crunch. And you can get it from my GitHub repository. I know it's important to have a demo, but the session time is limited, and I want to allocate more time to the question and answer, so sorry for that. And thanks to these people, without their help, this research could not have been born. And thank you all for your patience. Thanks.